And now on to the topic that everybody always loves the most, inexplicably. Black holes. So what is a black hole? Well, basically, we had the Chandrasekhar limit for white dwarfs. If you exceed that, you get a neutron star. And that was basically when you could overcome electron degeneracy. The similar situation exists for neutrons. At some point, you overcome neutron degeneracy, and you can keep collapsing. And so you can't have a neutron star above about 3 solar masses, because above that it will not, the temperature is such that you won't get neutron degeneracy, and it'll just keep on collapsing. It's actually, there isn't a mechanism to stop it. So basically, once it starts collapsing, theoretically it should keep collapsing forever and ever until it is infinitely dense. It turns out it's very difficult to investigate, so it's hard to test that hypothesis. But basically it becomes a singularity. It is collapsing to a single point, and that is what we call a black hole. So escape velocity is greater than the speed of light, so nothing can escape, not even light. But that allows us to define a kind of radius that's related to a black hole, even though the material within it may be much more densely compacted. Doesn't matter. This is kind of a limit that is, for all intended purposes, the surface of a black hole. So we're going to set our escape velocity to the speed of light and see what happens. So remember, escape velocity is given by the square root of 2gm over r. So I've just squared it and rearranged it, and now put in the escape velocity as the speed of light. So we've got a relationship between the radius, the mass, and the mass for a black hole. So if we've got something that's the mass of the Earth, for instance, we end up with something that has to be compacted down below a centimeter. So basically, it's about 1/3 of an inch. You have to get the Earth compacted down to 1/3 of an inch. So it's pretty dense. But don't let the density fool you. You have to be very careful how you think about that, and I'll come back to that shortly. If you wanted to have a black hole that was the size of the Earth, then we can just rearrange that equation to get the mass back out. It would have to contain 2,000 solar masses. And so this radius, this limiting radius, which is the point at which the escape velocity is the speed of light, is called the Schwarzschild radius. And it's given by the equation we just derived. So you've got the gravitational constant and the mass, and then the Schwarzschild radius is easy to calculate. So remember, nothing can escape from this once you get inside the Schwarzschild radius. But that gives rise to this idea of an event horizon. So, like I said, this singularity, this thing is collapsing down to nothing. But until you are beyond this point, you are within the event horizon. You're within the zone where the escape velocity is greater than the speed of light. Nothing can escape. And this is just to give you an idea of that relationship. So here we've got the Earth. The Sun would have to be compacted down to 3 kilometers across. Even a star that was 10 solar masses has to be only 30 kilometers across. Remember that 3 solar masses would be kind of the low mass limit for a black hole made by the collapse of a core collapse supernova, and it would be only 9 kilometers across, so a little smaller than a neutron star, in order to actually be dense enough to make that happen. Now, I want to consider a 500 solar radius star that has the same average density as the Sun. Okay, so here I've got, density is just mass over volume, and so what I'm going to do is I'm going to say, okay, if I've got a 500 solar radius star, but it's got the mass density of the Sun, this is the mass density of the Sun, so I'm putting this in for rho, I do a bunch of cancelling, I can basically calculate what the mass has to be. So for a 500 solar mass star, it basically goes as 500 cubed. Sorry, a 500 solar radius star, I have to have 500 cubed solar masses. And then we can plug that in to get the Schwarzschild radius out. And it turns out to be not much. It's actually bigger than the size of this thing, but not much. And so you can see here we're in a zone where it's not something that's dense. Remember, this is the same average density as the Sun, and basically we don't have 500 solar radius stars that are this density. But if you did, this would be a very, very massive thing. But it would be, the average density of the object would not be any much different from the sun. So don't be fooled into thinking it has to be super dense. So remember, we've got a neutron star, and if it exceeds, the core exceeds 3 solar masses. And again, if you've got a neutron star in a binary, you could add more mass and cause this to happen too. Then eventually you get to a point where light cannot escape and you've got a black hole. And we've got the Schwarzschild radius, and we've got how this all fits together for defining an event horizon. Now, there's another way of looking at this, which is how mass affects the shape of space. So I want you to consider, it's a little bit of a thought experiment. So I've got a table here, and it's got like a rubber sheet pinned to it, and I can put a weight on it. So I'm going to start by putting on a basketball. And I've got a basketball, and I put it onto the table, and it causes a little bit of a dip like this. Okay, so what that means is that if I want to put something in orbit around it, I basically have to run it around and have it so it has the right energy, so it keeps going around and around. And if it was a frictionless table, I could do that, right? I could make it so it would just keep going around and around. And how fast it would have to go would depend on how close to this it was, and you could get all of the orbital parameters that you need. Now let's consider that I've taken my basketball and I've now made it a tennis ball. Same mass, but it's now a tennis ball. So it's denser. And so I'm going to have a bigger dip. And now let's consider that I've taken that tennis ball and turned it into a golf ball. So I get an even deeper dip. So now I've got this deep dip. Now if I've got a planet out here, it's going to be going around here, and it's going to have to sustain the right speed. But it's not until you get fairly close to the thing that's causing the dip that's going to fall down. If I send my pool ball here across the table, it can go around and come over here. So it won't go straight across like it would if it was a flat table. It'll be deflected, but it will not fall into the hole unless it gets beyond a certain close to a certain point. And this is also true for black holes, and this is how we can think of what black holes are doing. So here you can see this is the idea of you've got this dip, you've got light that's coming from a star, and it gets bent by coming past an object. And so what it means is that if we could see stars during the day, or we look at them during a solar eclipse, we can see that the star looks like it's here when we know it's really here, because normally we're looking at it when we're not looking towards the sun. And this is one of the best tests of this idea, because we can do this, and it has been done numerous times when there have been eclipses. And so we can actually test this idea. And so basically what you've got is you've got the sun in here, and here's the surface of the sun, and as long as you don't get too close, you're not going to fall in, right? You're going around and around and around. This is actually for a 5 solar mass star. Here you've got something, it's a 5 solar mass star, but now it's made so that it's such a small thing that it makes this dip infinitely deep. If you're out here, it's not going to make any difference to you unless you approach this thing. And even then, it'll bend your path, but unless you actually start to come really close in, it's not going to make much difference. And so consider that we've got the sun, it's 1 solar mass, and we are orbiting it. If we were to turn the sun into a black hole of exactly the same mass, we would not suddenly fall into that black hole. We would keep orbiting at the same rate we are now. We'd all die because we wouldn't have light, but that's a whole other issue. From the point of view of being sucked in, you have to be pretty close in before that has an effect. Now, this leads to some interesting things, though, because we've talked about tidal forces and Roche lobes and Roche limits. What happens when you have a black hole, though, is that because the gravity, the mass is contained in such a small space, that you get really intense tidal forces, and so you can rip things apart much more easily. And so we're going to talk a little bit about that. So if you think about, I've got an astronaut and it's descending towards a black hole. And so if it wasn't in the vicinity of a black hole, this would be my astronaut. But as the astronaut is lowered down towards the black hole, the feet are going to experience a bigger pull than the head, because it's significantly closer. Remember when we did tidal forces, the issue for the moon is that there's a difference between the forces, so the pull on one side of the moon versus the other. Same for the Earth. One side of the Earth versus the other is being pulled more by the moon. Well, here, one side of the astronaut is being pulled more than the other. But at the same time, you can see it's being squished in this horizontal direction here, and that's because you can think of it as being the gravitational field lines. That you've got this gravitational field, and you've got them radially expanding from the black hole, but that means that they get closer together really, really fast. So you get stretched out and squished together at the bottom, all at the same time, and it's called spaghettification. Isn't that lovely? Because of the energy that's needed to escape from a black hole, it turns out that even light has some issues. And so light can't slow down. You've got a photon, it moves at the speed of light. That's what happens. But if you've got a photon that needs to use some energy to get away from that black hole, so it's not beyond the event horizon. If it's beyond the event horizon, it can't get away. But it's close to the event horizon, and now it's trying to get away. It starts off as, say, an X-ray photon, but it has to use some energy, and so it can increase its wavelength, and it becomes ultraviolet and then visible, or if it's a visible photon, it may go from infrared to radio. And so what you're getting is this effect of the light by trying to escape from the black hole. And so that's a really useful thing to be able to look at. And so when we're looking at something close to a black hole, there should be a significant redshift. It's called gravitational redshift because it's changing the wavelength of light because of the gravitational field and not because of a Doppler effect. It's not the motion. But if you're on a probe, and you're not going to see that. So if we go back to the image here, I've got this probe, and when it's here, it's, say, giving off a visible light beam back to whoever's watching it somewhere over here, but that's going to be a radio wave by the time it gets to where it's going. But this thing won't perceive it as a radio wave, it will perceive it as a visible wavelength thing. So what's inside a black hole? Well, we have no idea. There is no way to test that. There's no way to look inside of it. The current theories out there, relativity, all basically say that the mass has to collapse to a radius of 0 and have an infinite density, but that's unlikely. But since all it has to do is collapse within the black hole event radius, doesn't really matter what happens inside. We can't look at it. So until we can find a way to probe those conditions, there's not a lot we can do beyond understanding what happens close to it. So we can look for these things in space, though. We can't see them directly because no light is escaping, but we can infer them by their interaction with other things. So for instance, let's say we've got a companion, we've got a binary system, we've got something that is small and compact and we can't see it. But if we can see the bigger object, we can work out what the total mass is. And if we can estimate what this one is, right, we can work out what the motion of this object is. We don't know exactly where this one is, but we know that it's moving around. If it's got a hot accretion disk, we can actually see it moving around as well. And that means that we can actually use this to work out its mass, and that means we can say whether it's a neutron star or a black hole or whatever. And if it's bigger than 3 solar masses and very small, then it's got to be a black hole, because there's nothing else it could be. You also get weird lensing effects. So here we've got a black hole in front of a star, and what we'll see is that we'll get a very weird image of this object because the light will get distorted in this way. So you'll actually see a very distorted image as a result of the black hole. And if the black hole is moving with respect, so if this is in a binary system, it would move around and we'll see this okay, and then it'll be in the way and we'll get this distorted image, and then we'll see it back again. And it'll also distort other things. So if we're looking from over here, it will distort other things in the background over here. We can infer its presence from that. Say we can get an accretion disk. If we have an accretion disk from a hot companion onto a black hole, we will get X-rays just like we did with a white dwarf, and that will allow us to do some interesting modeling to figure out what's there. And so here we've got a whole bunch of black hole candidates. These are all in binaries, and this allows you to determine their masses, and you can see here they're all more than, except for possibly that one, which has a range going down to below 3 solar masses. But that means that we can basically say there's a compact object, and it's more than 3 solar masses, must be a black hole. So there we go. And that's where we're going to leave black holes.